This is AP Calculus 7-1, Modeling Situations with Differential Equations. And in this lesson, we just have to remember what it was that we dealt with when we did direct and indirect or inverse variation. The problems are going to say something like, one situation is directly proportional to another situation, or something is inversely proportional to another situation. So we're using inverse and direct variation for these. Usually, in most of these, we're dealing with direct variation or directly proportional. So just to do a quick review of direct variation and its formula, when we deal with direct variation, K is our constant of variation. So it will be consistent throughout the entire problem that we're talking about. And if it says y varies directly as x, the formula for that is y equals k times x. You were first introduced to this in Algebra 1, and then in Algebra 2 you should have done a little bit more. We expanded it from direct and inverse into joint variation as well. And then here, this one says y varies inversely as x, or it could say y varies indirectly as x. And that formula is y equals k over x. And these are the models that we will use when we're dealing with directly and inversely proportioned problems. So just to do a quick example, and a lot of these examples are dealing with exponential growth and decay, and these are very, very common when you're dealing with AP Calculus test problems. A car travels on a linear path. The car's position is given by P of t, where t is measured in hours since it started traveling. P is measured in miles. The car's acceleration is proportional to the square root of the time since it started moving. Write a differential equation that describes this relationship, where k is a positive constant of proportionality. We know that since this is directly proportional, that our formula is going to be in the form y equals kx, our constant of variation k. And here they're giving us some variables to deal with. It says a car travels a linear path. The car's position is P of t, so that's an important variable. They also say here that P is measured in miles, which means P of t is measured in miles. Those two things are interchangeable. T is measured in hours since it started traveling. The car's acceleration, so acceleration is proportional to the square root of time. Now, think about that, the square root of time. Wouldn't that be the square root of t? So we know somewhere in the problem we're going to need a square root of t. And the car's acceleration, now let's think about what that means. If P of t is the position function, let's see, that's position, then wouldn't P prime of t be the velocity? And so then wouldn't P double prime of t be acceleration? So if they're saying the car's acceleration is proportional to the square root of the time, then our formula would be P double prime of t is equal to k times the square root of t. If we're talking about differential equations, if P of t is the position function, another way to express the velocity of P of t is dp over dt, the rate of change of the position function over time. And then for acceleration, the second derivative using that notation would be d2p over dt squared. So this denotes the position function, this denotes the velocity function, and this denotes the acceleration function. So another way this could be expressed is d2 of p over dt squared equals k square root of t. And either one of those would be acceptable. Bacteria in a culture increases at a rate proportional to the number present. All right, in this one, they don't give us any variables, so we have to determine what our variables are going to be. So bacteria, I'm going to let B equal the number of bacteria present, and it increases at a rate. Now let's think about what that means. Isn't that the derivative of what we have? So if B is the number of bacteria present, then wouldn't the rate of change of that be representing the situation we're talking about? So if it increases at a rate proportional to the number present, this is a direct variation problem, and if the rate of change is proportional to the number present, then that is K times B, and that would indicate that this is equal to the rate of change, the increase. And so the rate of bacteria changing would be dB over dt, the rate that the bacteria increases. In this one, I've taken this from one of the AP videos that they have. I just thought this was a great type of example that you might see in an AP test or an AP practice test. So I thought this was a good one. A rumor spreads among the population of N people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. If P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model the situation with respect to time t, where K is the positive constant? Well, if N equals the number of people, total number of people in the population. And they told us that P is the number who have heard the rumor. Well, if P is the number of people who have heard the rumor and N is the total number of people in the population, wouldn't N minus P be the number who have not heard the rumor? So P is the number who have heard the rumor, N minus P is the number who have not heard the rumor. So let's go back up here and see what it says about this. A rumor spread among a population of N people at a rate proportional to the product of the number of people who have heard the rumor, so that's P, to the number of people who have not heard the rumor, that's N minus P. If it's directly proportional to this product, then that product needs a K in front of it. That will be equal to our differential, dP over dt. So we can compare this to what we've got over here. I would say it's probably B, but I would double check and make sure the others don't match. A particular disease can spread in one of four possible ways. Let P of t be the number of individuals infected at time t. Let P sub 0 represent the initial number of people infected, which is the same as P of 0. And suppose the total population is 200. The four models are given below. So for model 1, dP over dt is equal to K, that's the constant. Model 2, dP over dt is equal to K times P. The rate of change of P is directly proportional to the number in the sample. Model 3, the rate of change of P is directly proportional to, if P of t is the number of individuals infected, then wouldn't 200 minus P be the number of individuals not infected? So the change in P is directly proportional to the number not infected. And then here, the change in P is directly proportional to the product of the number of those infected times the number of those not infected. So we need to match these with the models here, is what it's asking us to do. So the rate at which the population is infected is proportional to the number of individuals infected. And they told us that P is the number of individuals infected. So that would be model 2. The rate at which the population is infected is constant. Well, the only one with a constant is model 1. So that would be model 1. The rate at which the population is infected is proportional to the number of individuals infected, that's P, and those that are not infected, that would be 200 minus P. So that would be model 4. And the rate at which the population is infected is proportional to the number of individuals not infected. That would be model 3. The rate of change of the intensity of a response R with respect to the intensity of a stimulus S is inversely proportional to the intensity of the stimulus. And this differential equation is known as Fechner's law. I'm not sure I'm pronouncing that correctly. So if R is our variable of integration, we're doing this with respect to the stimulus S. So we're talking about dr over ds being our rate of change. So dr over ds is inversely proportional to the intensity of the stimulus. So let's see, the rate of change of the intensity, that's this, the rate of change of the intensity, is inversely proportional to, if it's inversely proportional, that would be k over something, and it's inversely proportional to the intensity of the stimulus. So that would be k over S, they said, was the stimulus. So we've written that differential equation. Here, let S represent the total sales of a computer product, T years after the product was introduced. So S is the total sales over time. So the rate of change would be the change in S with respect to time. The total sales of the computer product are growing in inverse proportion to the natural log of T plus 1.4. So ds, the change in S over time, is inversely proportional. So we have k over that natural log of T plus 1.4. And so that's it for this section. So you're going to practice modeling some of these direct and inverse variation situations. And then that leads into more word problems involving differential equations later. So first we're going to learn how to set them up. Then we're going to learn how to verify some. Then we will talk more about how to solve differential equations. And then we will apply those to some real life type of examples. This is where the calculus starts really dealing with a lot of different sciences and things like that, where we can really use calculus to demonstrate real life situations.